Welcome to the channel, guys. In this video, we'll be discussing about coupling reaction of REACTIONS salts. Right, the diazotization video we discussed about the preparation of diazonium salts, which looked something like this, and we had aryl diazonium salts. So here is that, and we prepared them. We prepared them from aniline, these types of compounds. Fine. And in that video, I told you about that these diazonium salts, they are of this can be chlorine or bromine, or this can be chlorine or bromine. Fine. So in that video, I told you these are of synthetic importance. Now this coupling reaction, this is another synthetically important reaction of these REACTIONS salts. So what happens is that in this reaction, we take these this REACTIONS salt or diazonium salt simply, and we react it with either with phenol or with arylamine. And what we get is an azo compound. An azo compound. Fine. Now, what is an azo compound? Azo compound. What is an azo compound? You can see azo compounds, they are compounds in which the functional group is this one, and double bond N, and these are the R groups. Fine. This is an azo compound, general representation of an azo compound. So this is the product of the coupling reaction of REACTIONS salts. Now, in place of R in aryl compounds, we have AR bonded to N, double bonded to N, and single bonded to AR dash or AR simply. Okay. So this is our reaction that we are going to carry out, right? Now, first of all, let me tell you that it is nucleophilic substitution reaction, and in this nucleophile is this molecule, and it acts on the ortho or para position of pH molecule, that is phenyl molecule, right? Now let's see how it happens. First of all, let me show you one thing about this diazonium salt. Here I take a diazonium salt. Fine. It has two resonating structures. Triple bonded to N. This is the first resonating structure. Fine. Positive charge over here and a lone pair of electron over here. But another resonating structure is also there. It is this bond pair. It converts into lone pair of this nitrogen. We get a positive charge on the other nitrogen. Fine. This is the resonating structure. Fine. This is the positive charge on this one. Also, there's a lone pair and there's a lone pair as well. Fine. So these are the two resonating structures. Now in this reaction, this resonating structure is taken into consideration. I will show you how and where does it act. So this acts as electrophile. Fine. This acts as electrophile. This acts as electrophile. Also, the second thing that we have to make sure is that this phenyl molecule, sorry, not phenyl, this phenol molecule or arylamine molecule, they are activated at their ortho position for nucleophile. I will show you what that means. For example, I take a phenol molecule like this. I will draw a phenol molecule here. So this is a phenol molecule, 3 double bonds and OH connected to it. Fine. What happens is that, let me raise this line over here because so 3 bonds are like this. Fine. So what happens is that this OH, it has 2 lone pair of electrons. It converts one of its lone pairs into this bond. We get something like this. Let me draw the resonating structures of phenol, that you can completely understand how the reaction goes on. Fine. This molecule, this bond pair, it converts into lone pair of this carbon. Fine. So we get something like this: double bonded O, positive charge on oxygen, and H. Usually this reaction is, we say that NaOH can be added to this, which will create a phenoxide molecule, which looks something like this. Fine. An oxide molecule looks like something like this, and then this goes here, but we can show this as well. Fine. So don't worry about that. Erase this all. Fine. So this, there's a lone pair now over here, and a negative charge. Fine. This bond pair is here. This is here. Now what happens is that this goes to this position, and this one goes to this position. Right? We get something like this. Let me draw the resonating structure. Fine. So here double bond is created. Here double bond was already present. Negative charge and a lone pair over here. Fine. So positive charge on this oxygen over here. Fine. And H is already connected. Fine. So this is the third resonating structure. Now what would happen is that this will go here, and this one goes to this position. And we get something like this. Let me draw it. Fine. And negative charge over here. Double bond over here. Double bond over here. And double bonded oxygen. Positive charge on oxygen, and H is already connected. Fine. I hope you understand what's going on here, because these are resonating structures which you can draw, I hope, because that is already learned by all of you, I think. Suppose that. Fine. I presume that. So the last one will be this one going here, and this going back to this oxygen. Fine. So we get something like this. These are the resonating structures of this phenol molecule. Fine. Wait. Now, if you see in these resonating structures, negative charge develops on this ortho position and this ortho position. Fine. And also negative charge develops on this para position. Now, if a nucleophile comes in, that is a molecule which is, in search of electrons, it will most likely be going to either this position. You draw it with a different color, mark it with a different color. So it will be either going to this position, or this position, or this position. But what happens is that this OH molecule, it provides steric hindrance, fine, at this ortho position and at this ortho position. Fine. So these are sterically hindered positions. So the nucleophile coming in, which is also a bulky nucleophile because it's a very big thing, you can see. So it comes in this position. Fine. Let's see what happens. Let's take this resonating structure over here, and let's draw it like this. So this has the double bond over here, double bond over here, negative charge over here. I have drawn it inverted so that you can understand it well, much better. Fine. Double bonded oxygen, positive charge, and H. Fine. So this is the resonating structure of phenol ring, which will be reacting. Fine. Now what happens is that also H is there. Just a moment. Also H is there, which I will be showing you later on. Let me also draw our nucleophile, which looks something like this. Fine. The nucleophile looks something like this. N, double bonded to N, and a positive charge on this nitrogen, and a lone pair over here. So what happens is that this nucleophile, let me mark it with this electron pair, it will be attacking here. Fine. We'll be getting something like this. Let me draw it. So an azo compound is almost ready now. Just have to do the resonance, and the job will be done. Fine. This is the N double bond N. Fine. Ready. And double bonded N. Now a bond is established with this phenol ring at the para position. Fine. I hope you understand it. And OH double bonded O, positive charge on oxygen, and H is already present. Fine. Now what happens is that at this position, let me raise a thing first of all. Right, let me write it clearly so that you can understand it better. And double bonded N. Now this nitrogen has a lone pair, this nitrogen has a lone pair, no worry about them. But here you can see here is this hydrogen as well. Fine. So what happens is that in order to achieve stability, or in order to what we call as get more resonance, get it again back to, aromaticity. So what we do is that this H leaves and this bond pair, it goes to this position. And so we get something like this. Just a moment. I'm having a hard time drawing them, but I will try my best to draw them perfect. Fine. So this is what we have got. Fine. And over here we got now this thing. So this is this was already present, double bonded O. This thing was already present. Fine. Positive charge on this oxygen. Fine. And this double bond was also already present. So when this bond, its electron pair came to form this bond pair, this one goes here. Fine. So we get something like this, a negative charge and a lone pair over here, and this one over here. Fine. I hope you understand it. Now again, this thing goes here, this thing goes here. So we get something like this. Double bond, double bond, double bond, N, double bond, N, also this molecule. Fine. I hope you understand it. This, and OH. Fine. Now here you can see OH. Now here you can see our azo compound. It has been formed. Fine. This H is also present. So this is our azo compound. Let me write it down. So what is the product of this, coupling reaction? It is azo compound. Fine. Now in this reaction, you must be knowing that these azo compounds, you might have heard about azo dyes. So these reactions are of synthetic importance for many commercial products, something which we call as dyes, right? Dyes, a lot of dyes are produced by this reaction. So we can say that these reactions are of synthetic importance. That's why we study them. And this is all about the reaction procedure, right? First of all, our nucleophile is developed from the diazonium salt, which looks something like this, and double bonded N, and this is the first step. Fine. This is our nucleophile generation. Then it reacts with our phenol ring, which is activated at ortho and para position, attacks this compound. Fine. Attacks this compound, positive H. Fine. Now this attacks it. We get something like this, N, double bonded N, single bonded this molecule. Fine. Now let me draw the bond like this. O positive and H over here. Fine. This happens. Now this H, it is removed as H positive, and this goes here. Then this goes here. Also, then after that, the negative charge that will be developed here. This goes here, and it goes here. So we get a final azo product like this. It's in nutshell. We can say that. Okay. So here N, double bonded N. Also this ring. Fine. And this ring over here, this, and OH over here. I hope you understand what we have done. Right? So here you have to understand that if the para position, if it is already occupied, then this nucleophile, it can attach to the ortho position as well. And at that time, for example, let's take a molecule like this. So this is the molecule that we are taking into consideration. This is OH over here, and CH3 over here. Now you can see the para position is already occupied. Where will the nucleophile go? So simply this ring, it's not only activated at this para position, it's activated at both the positions, that is this ortho and this ortho position as well. So at this in this situation, the nucleophile will be going to this position, right? So we'll be getting something like this. We compare it, we'll be getting something like this. If I show you OH over here, let me draw it with white color so that you can get it much better. Fine. So we will get something like this: double bond, double bond, double bond, CH3 over here, OH over here, and also N, double bonded N, and also the ring attached to it already. Right? So this is all about coupling reaction of diazonium salts. What happens in them? They are preceded by nucleophilic substitution reaction, and in them the final product is an azo compound, and that azo compound that usually is a dye. That's why they are of these reactions are of commercial importance. That's why we study them. And the nucleophile, it acts on the para position, fine. But if the para position is occupied, then it will be acting on ortho position, fine. These are key points about it, and it's a very simple reaction. That's why we didn't have to make this video too long. I hope you understand it. Make sure to subscribe to the channel Chemistry Cracks in order to get more videos like this. Thank you.